Welcome to the mind map series, and we'll be discussing this chapter, which is the dual nature of matter and radiation. In the last chapter, we had discussed that light has dual nature, that it may behave as particle at certain points in certain experiments, and it may behave as a wave as well in certain experiments. So this is called dual nature. But later scientists also discovered this property also in electrons and other subatomic particles. So it was later hypothesized that every matter has a dual nature. It behaves as a particle as well as a wave. Although the wavelength may vary, it may vary that it may reduce to very infinitesimally very small level, such that it is not observable the wave motion. For example, see, uh, if this is a wave, it is very easy for you to realize this one. But as the wavelength, this amplitude decreases or the wavelength increases, it might look something like this, right? And this is still something manageable, some manageable wavelength. But if it increases further, it appears to be a straight line, but still it is a wave having very long wavelength. All right. So this is the wave nature of the particle that I've explained here. Now, this emerged from the quantum theory of matter. Quantum theory. This was initiated by a very famous scientist, Max Planck. He gave that energy in any particle or anything if it has some energy, then that energy has to be quantized. Quantized means quantized means it has to be n number of energies. Means there is a limit before further to which you cannot divide the energy further. So basically he said that energy is quantized, and any energy that any particle has, energy at any particle A has an energy which is a integer multiple of the quantized energy, the least amount of energy which is possible. It is not like any particle could have 1.2 amount multiplied by this smallest unit. No, it only has to be 1, 2, 3 things like that. So this is called energy quantization, that the energy has been quantized or it can only exist in the multiples of a certain number. Now this number that he defined was Planck's constant. Planck's constant, this number, that every energy has to be multiple of this Planck's constant. And he said that this where the Planck's constant is equal to 6.626 multiplied by 10 to the power minus 3 joules. This is the Planck's constant. All right. Now, if that is clear, then we have something that the energy of any particle is equal to this Planck's constant into mu, h mu. This is quantization and Planck's constant is h. We represent with the number h. Now, energy of any particle or any, this is for electromagnetic radiation, EM radiation or electromagnetic waves. Energy is equal to h by mu. All right. Now, this is frequency, right? Frequency. So it is simply frequency multiplied by a fixed constant that you do you'll get the energy that is associated with that uh, EM radiation, or energy of that particle, photon, energy of a single photon, of a photon. When you convert this in form of wavelength, what will happen? First of all, um, velocity of light is equal to wavelength divided by time period, or wavelength multiplied by frequency, right? Frequency, or it can also be represented in the form of mu. And what is the speed of light? We represent it with the number c, that has the value of 3 into 10 to the power 8 मीटर पर सेकंड. अभी ये हो गया है तो c इज इक्वल टू हो जाएगा सिंपली लैम्डा इंटू म्यू, राइट? So from here mu is equal to c by lambda. So energy is going to be simply h multiplied by mu, which is c over lambda. In the form of wavelength, you can remember this one, or much easier to remember is this one. So this is the energy associated with any photon, a single photon. I think we have already discussed these things. The interference can be explained by wave nature. In the last mind map, we have discussed this one explicitly. And sufficiently low wavelength, it behaves as a particle. Actually, every light can behave as a particle. Light particles having defined energy and definite linear momentum. We have also talked about, or we will talk about in the structure of atom chapter, that this linear momentum is also quantized. And energy of each photon, we have discussed this one. And momentum, I think we will discuss momentum here. We'll discuss momentum in the de Broglie wavelength, no problem. Now, if this is about radiation, we have discussed that, then I think we can go ahead and talk about this experiment. Davison German experiment. What they did was, they took some crystal, a pure crystal of any material. Actually, they took, I think the material they took was nickel crystal. Okay, no problem. And what they provided was um, electron particles, electron beams. And what they observed was, it was left to pass through the crystal, and before after that there was a detector, and it interacted in such a manner that it formed certain high points, or certain points of high intensity and lower intensity, and it was formed in such a manner that you might observe that result of Young's double slit experiment, it was almost like that. Actually, Young's double slit experiment can also be performed with electrons. So this was observed, confirming that electron 2 is wave. But we also know that electron is particle. That is pretty much obvious from our whole scientific experiments that we have done. So what we see from here is, electron is acting both as a particle and a wave, same as the light. So we can say that even electron is a wave, or dual nature it has. This was possible for electron, but for higher masses, the pattern is such mixed that it doesn't appear as much to be very clear. So what it was hypothesized after this, that every matter has dual nature. The particle nature we are very familiar with, but every matter, including me and you, have wave nature as well. So from here, there was a scientist called de Broglie. who gave this formula that for any matter, what should be the wavelength of the wave that it represents. He said that this was lambda is equal to simply h by p, h by p, where h is the Planck's constant, p is linear momentum, and lambda is the de Broglie wavelength. Basically, the wavelength, the particular material in question, when it follows the wave, then what is the wavelength of that particle or that wave, right? So this is de Broglie wavelength, and for electrons, you can find it using this thing. Electrons were found to have a wavelength of 1.67 angstrom. That is not important. It's just that this formula is important. De Broglie wavelength is equal to h by p. In the using this formula, can we find out the momentum of a light particle, photon? Of course, because we already know the lambda for that, and from de Broglie wavelength, that should be the lambda de Broglie wavelength of that light. So it is simply h by lambda. This is the momentum carried by a photon. Even if it doesn't have a mass, it has momentum. So yes, this was what I was talking about, that I said I will discuss later. Momentum of each photon is equal to h by lambda. Now, if that is clear, then I think even this could be represented by the energy contained in the photon, because h nu by lambda mu nu, you just multiply nu by on both sides. What is h nu? It is simply energy contained in a photon, and lambda nu is simply speed of light. So this is what they are written. They have written. This is factual information, not really important. And this is the de Broglie wavelength. And you can find out using h by mv. I've already told you that this is a linear momentum, right? So lambda is equal to h by p is equal to h by mv. And how can you find mv? Isn't mv is equal to mv square is equal to kinetic energy, right? So m square v, sorry, half mv square, m square v square by 2, sorry, m square v square multiplied by 1 by m, and multiplied by 4 divided by 4. What is this? Just a second. I think we could use a better derivation. Half mv square is equal to ke, right? Now I think they have taken only one e, and mv is equal to h by lambda. So what you can do is, yes, they have just converted mv in form of mass and kinetic energy. How you can do that? You can convert this to be divided by uh, the whole thing is squared. Then you have m square v square is equal to h by lambda, and when you multiply this by mass and divide this by mass, it gets cancelled out and you are left with mv square, and you do half mv square by 2 and multiply by 2. So basically this part is half mv square kinetic energy, so 2m into kinetic energy is equal to h by lambda. The whole thing is squared. When you take the root, then it becomes h by lambda, and lambda becomes h by root under 2 k e into m. This is what is written over here. De Broglie wavelength, there could be several methods to find it. I think only photoelectric effect is left. Einstein is mostly famous for theory of relativity, right? But he was given the Nobel Prize for not theory of relativity. It was given for photoelectric effect, because uh, although it was much more revolutionary, the theory of relativity, but several scientists at the time disputed it, that there is no way to prove it. But all of course, it has been proven time and again in the modern times. So let me discuss over here. First of all, this experiment that these two guys, Hertz and Leonard, what they did was, if there are two metal terminals, and let's say you have battery, all right, or maybe opposite sides, that would be more easier. Yeah. Now, the current must flow. If this was connected, the current must have flowed in this direction, right? In this direction. And what is the carrier of current? That those are electrons which flow in this direction. Electrons. Now, the only thing that is obstructing the the current is trying to flow. The electron is trying to flow, but there is no conduction between them, so it can't flow, right? What they did was, they covered it in a setup which has vacuum, so that it is very very clear that there is even the air particles can't conduct this electricity. Now what they did was, this is vacuum, there is no way that electron can jump, right? The electron can't jump, although in quantum physics electrons do jump over certain barriers. It is not important now. See, what the observation was, that the electrons here are not able to go on that side, right? And hence can't conduct the electricity. What they did was, they provided, oh, just a second, ray of light. Some ray of light fell on the surface, and what happened was, there was some conduction. The electrons got ejected and they conducted the electricity, and some deviation was found on this ammeter or galvanometer. What it gave was that normal surfaces, if there is a normal surface of any metal, then it can't emit electrons, right? But when certain light of certain intensity or wavelength tries to uh, interfere with the metal surface, then some electrons are ejected. Electrons. This is called photoelectric effect. Photo because it is due to light, and electric because the electron is the one that is getting ejected. Effect. All right. Now we'll talk about something. Uh, is it very easy, or does it take some energy to for photoelectron or this electron to eject? Of course, because the atoms that are there, although they have electrons in the outer shell, no problem, but still there is some attraction between them and some potential energy. Only when you provide enough energy to overcome the potential energy between the electron and the nucleus, only then the electron can come out, right? That is exactly what is happening over here. So this So it means that any amount of energy cannot do this, right? The energy has to be uh, a threshold of energy, right? Threshold must be clear. Threshold of energy must be cleared by the light. It means the light must have a minimum amount of energy to knock out the electrons out of the outer shell of the metal. So this this threshold of energy that is required, above which the photons must carry so as to knock out the electrons, is called work function. All right. So this is called phi. Now, can we find out the threshold or threshold wavelength? Threshold energy required is work function. And what is the light that will carry this much amount of energy? Hc by lambda is equal to phi. If the ray of energy or the photon has enough energy to balance out the work function or the amount of energy required between the to knock out the electron, or the amount of potential energy between the electron and the nucleus, only in that case the electron will get knocked out, and we'll call it photoelectric effect. Otherwise there is no photoelectric effect. So this is the threshold. Threshold, or you can say h nu threshold is equal to phi. Although this is more prevalent because we usually represent the light in form of wavelength. We give oftentimes you will find that the wavelength data has been given, not the frequency. So this you have to remember for the threshold. Now, before this, if the lambda is higher, energy will be lesser and no photoelectric effect. No photoelectric effect. Photoelectric effect. But let's say if lambda is lower, the energy in carried by the photon is higher, then of course there will be photoelectric effect. But where is that extra energy going? Let's say you have certain threshold of energy required, and now you give a higher energy to balance out this much amount of energy. Then this much amount of energy is still left, right? Where will that go? The energy cannot get lost. Energy can neither be created nor be destroyed. So it will get converted in the form of kinetic energy. Let's find the kinetic energy of the this thing. Kinetic energy is equal to um, the amount of energy that has been given by the light, hc by lambda minus work function. All right. So this is kinetic energy that is that the electron gains after getting knocked out. Now, when you want to find this is kinetic energy, right? Now, this will be simply half mv square is equal to hc upon lambda minus phi. Now, there is something called stopping potential. Basically, let's say there is an atom, nucleus, electron. You give you gave a light such that electron got ejected with some velocity. So it is going with some velocity. Now it will have some velocity, right? What is the potential needed to stop this electron from flowing? Then what you have to do is basically you give it a potential difference such that it is negative and this is positive. Electron is flowing in this direction. It will stop this basically. So yes, this is called stopping potential. The potential energy or the potential that you must provide to the electron so as to counteract the kinetic energy or to stop the electrons from gaining some velocity. This is called stopping potential. And what was the energy that the electron had, kinetic energy? It was simply hc minus lambda, sorry phi, right? Hc by lambda minus phi, and this is the amount of kinetic energy the electron possesses. Then you have to reduce this, or reduce this energy, right? What you have to do is basically give a potential such that when you multiply it with the electron, the charge that is flowing is electron flow, right? So the charge on one electron is E. Then this is the volt that must be applied to stop the electron. So this V is called stopping potential, and this E is the charge on one electron. Charge on one electron. I guess this is clear now. The whole thing. This is not longer than this. The whole experiment. I think we have covered this one. Stopping potential, threshold wavelength, threshold frequency. We all did that. I think even this was clear. Yeah, we have covered all of this. And this experiment we also talked about slightly. We do not need to get into the details of it. Not required. All the questions will be solved by what we have discussed till now. All right. So now, I think all matter can behave. Yeah, we have already discussed this one. This is not required. Just quickly, this was kinetic energy maximum. Yeah, it is the kinetic energy, no problem. And hc by lambda, threshold frequency. See, k max is lambda v minus v naught. It is simply this same equation that they have did. Phi, what they have done is, see, there was this equation, right? H nu by threshold, or this thing. What they have done is they have plugged this in this equation. So kinetic energy is equal to hc by lambda given minus hc by lambda threshold, right? Threshold, because phi was hc by lambda threshold. So kinetic energy could also be written in the form of hc 1 minus lambda minus 1 minus lambda threshold. This is the threshold frequency, or sorry, threshold wavelength of light that is just enough to knock out the electron or cause the this photoelectric effect. In the format of mu, ke is equal to h mu minus phi. And what is ke? It is simply h mu. Sorry, not ke. It is phi. So k is equal to h mu minus mu naught, right? Frequency, threshold frequency. H view threshold frequency. So I can write it as naught or anything else. So h mu minus mu naught. This is going to be the kinetic energy. It is all just the same thing. You just have to know that how to convert one to the other. Then you will not have to remember multiple equations and all that they have done here. So yeah, when the lambda given is equal to the lambda threshold wavelength, then there will be no kinetic energy gained by the electron, hence no kinetic energy. And when lambda is greater than the lambda threshold, photoelectric effect will not happen, right? Because higher the lambda, the lesser the energy. So you are given lesser energy than that is required by the electron to exhibit photoelectric effect. So E will be lesser than this, no electron will come out, no photoelectric effect. And when you give it a lesser than or equal to, photoelectric effect will come out, or and this, not lambda naught, yes, lambda naught and the work function, they both depend on the nature of the material. All right, so this was photoelectric effect. It is mostly observed by the metals, because non-metals, whenever you give that much amount of high amount of energy, it rather burns out rather than giving electrons out of it. Okay, so mostly observed by metals. So this is all for this very small topic. Thank you.